In this example, I'll use a general linear f-test and a partial f-test to determine whether we can remove a subset of predictors from a model. We'll use the Peruvian blood pressure data, in which the response variable y is systolic blood pressure, and we have 9 potential predictors. First, we'll fit the complete model to all 9 predictors. And in the ANOVA table, we can see the sum of squared errors for the complete model is 2172.58 with 29 degrees of freedom. We can also see that 5 of the 9 predictors have relatively high individual p-values. What these tell us is, for example, for height, the p-value 0.355 indicates that we could think about dropping height from the model as long as we keep the other 8 predictors. 0.213 for chin suggests we could think about dropping chin as long as we keep the other 8 predictors in the model. So taken together, these 5 individual tests suggest that we may be able to drop all 5 predictors from the model, but remember, each time we drop one predictor from the model, everything will change. And so this doesn't tell us yet whether we can drop all 5. To do that, we need to test the null hypothesis that the regression coefficients for height, chin, forearm, calf, and pulse are all equal to 0. And to do that test, we need an F statistic. To calculate the F statistic, we can proceed in one of 2 ways. The first way is to use the general linear F statistic formula. To do that, we refit the model without those 5 predictors, and we obtain a reduced model which has this ANOVA table, where the sum of squared errors has increased to 2629.7 with 34 degrees of freedom, and we can put that information together with the information from the complete model and calculate the F statistic formula as follows. First, we write down the sum of squared errors for the reduced model. Then we subtract the sum of squared errors for the complete model. We divide that by the difference in the degrees of freedom. Then that's the numerator of the test statistic. The denominator is the mean squared error for the complete model. If we calculate that out, we have 457.12 divided by 5 in the numerator and 2172.58 divided by 29 in the denominator. And if we calculate that out, it comes to 1.220. To calculate the p-value, we use Minitab as follows: 5 numerator degrees of freedom, 29 denominator degrees of freedom, 1.220 for the test statistic. The area under the curve to the left of that test statistic is 0.675, so the tail area to the right, which is the p-value, is 1 minus 0.675, or 0.325. 0.325 is larger than our significance level alpha 0.05. So we fail to reject the null hypothesis. In other words, those regression coefficients for the 5 predictor terms could all be 0. In other words, we can drop those 5 predictors as long as we retain the other 4. So that's the first way of calculating the test statistic. The other way is to calculate a partial F statistic. To do that, we fit the complete model. So I need to put those 5 predictors back in now. If I click Options, I can change the sum of squares for the tests from adjusted to sequential. And now if we look at the ANOVA table, sum of squared errors is the same as it should be, but the difference is we have sequential sums of squares now. And to calculate the partial F statistic, I'm going to need to use the sequential sums of squares for each of those 5 predictor terms. So this is how we do it. So this is now using the partial F statistic formula. We add up those 5 sequential sums of squares. 1.68, 297.68, 113.91, 10.01, 33.84. We have 5 sequential sums of squares there. So that's the numerator, and then the denominator is the same as before, just the mean squared error for the complete model. And if I calculate that out, I end up with exactly the same as I got using the general linear F statistic formula. So 1.220, whichever way I do it.